For the second part of Chapter 3, we're going to be looking at Lewis structures and molecular geometry. So we'll start by talking about the Lewis electron dot configuration. So you can see a picture of a Lewis electron dot configuration in that white square off to the right. And what this is it's a carbon atom. So to write a Lewis electron dot configuration, we draw the element symbol, in this case carbon. Now those dots that are around carbon, those are representing its valence electrons. So the element symbol represents the nucleus and the inner electrons, and the dots around represent those valence outer electrons. Remember, the valence electrons are the electrons that are involved in bonding. If you look where carbon is on the periodic table, you can tell, based off where it is, that it has 4 valence electrons. So that is why it has 4 dots. Also notice, when we're writing the valence electrons, that we put 1 electron on each of the 4 sides of the chemical symbol. So we don't pair the electrons unless we need to. The electrons are negatively charged, and so they repel each other. So we don't pair them up until we have to. Looking at the electron configuration, you can see in that highest principal energy quantum level, there is a total of 4 electrons as well. So to draw Lewis symbols, you first start with the symbol from the periodic table. Then you imagine a box around that symbol. Each side is going to hold a maximum of 2 electrons, much like an orbital. For each valence electrons, you add a dot on the sides, making sure that each side only gets 1 dot before you start pairing. Only pair if you have to. Keep in mind that helium is the exception, because helium has 2 valence electrons and only has 1 s orbital. So here are some representations of each group on the periodic table and what their Lewis symbols would look like. So starting with lithium, we see it has 1 valence electron. Well, lithium is an alkali metal, so all alkali metals do have 1, so they look very similar to that. You can see the other groups' representations as well. Notice when we get to nitrogen, who has 5 valence electrons, that's when we're going to start pairing. So here's a periodic table representing the Lewis dot formations for all the main group elements on the periodic table. Notice that the metals, their total dots is the maximum amount of electrons that they can lose to form a cation. So all the alkali metals in group 1 have 1 dot, and they can lose that 1 electron to become a +1 charge. So we're tying it together with oxidation numbers. For the nonmetals, we're looking at the unpaired dots. So however many unpaired dots the nonmetals have, that's the number of electrons they gain to become an anion. Or it could also be the electrons that they share to form a covalent bond. So it really depends if you're talking about ionic bonds, in which the nonmetals would gain electrons because there's a transfer, or covalent bonds where they're sharing. So for instance, looking at nitrogen again, we see that nitrogen has 3 unpaired dots. So it gains 3 electrons when it forms an ion, forming an N-3 ion. Gaining 3 electrons to pair up those 3 unpaired ones makes it a total of 8, so it now has a full octet. In contrast, if nitrogen were in a covalent compound, it could form up to 3 bonds with other atoms in sharing those 3 unpaired electrons. So we're going to focus on covalent bonds, sharing electrons. Atoms can share 1, 2, or even 3 pairs of electrons. So when they are sharing just 1 pair, and when I say a pair of electrons, that means 2 total electrons. If they're forming 1 pair, sharing 1 pair, it's a single bond. If they are sharing 2 pairs for a total of 4 electrons, that's going to be a double bond. 3 pairs for a total of 6 electrons, that's a triple bond. When we write the bonds, we write them with lines. So a single bond is just a single line. A double bond we would represent with 2 lines. each line being 2 electrons, so for a total of 4. Triple bond would be 3 horizontal lines, each line representing 2 electrons for a total of 6. So let's look at the bond energy of single versus double versus triple bonds. So what bond energy is it's the energy required to completely break the bonds between two atoms. A single bond is going to have the lowest energy. Double bond will be next, and then a triple bond will be the hardest. Also, the bond length. So the bond length is going to be the distance between the two atoms. So notice bond length is following the opposite trend. What we're seeing is a single bond is going to be the longest, then double, and then triple is going to be the shortest. So a way to envision this is if you think of two atoms, so they're going to be spheres. So say you take two balls. You put a rubber band, just one rubber band, connecting the two balls together. So that would be a single bond. Well, that one rubber band on those two balls, you can pull that rubber band pretty far apart so that the balls are really far, a long distance from each other. Now, add a second rubber band to those two balls. That would be your double bond. Now it's harder to pull those two atoms, those two balls, apart. The bond length is shorter, meaning those two balls are going to be closer together and they're harder to break apart. Triple bond makes it even more difficult to break them apart and makes those balls even closer together. So we're going to use all of this information to draw what we call Lewis structures. And we're just doing these for covalently bound compounds. So here are the basic steps when we're drawing a Lewis structure. And these steps are also on a handout in your folder for this week. So first step is to sketch the skeletal structure using the symbols. So when you're going to be given a chemical formula. Once you have that chemical formula, what you're going to do is figure out how the atoms are arranged. What is connected to what? So to help you figure that out, you're going to take the least electronegative atom, and that's going to be your central atom. Now usually the least electronegative atom is the first one present in the formula. So for instance, if I were going to try to sketch out CH4, carbon would be my central atom. I would put the 4 hydrogens all around carbon. Why is carbon the central atom? Because it's first, but more importantly, because it's the least electronegative. And you can use your electronegativity tables to prove that. Next, hydrogen and halogens are usually terminal. What that means is hydrogens and halogens aren't going to be the central atom. Okay? Once in a while, you can see a halogen as being a central atom, but we're not going to see it in this course. So for now, don't put them in the middle. Okay? Put them on the outsides, the terminal positions. Carbon forms chains of carbon-carbon bonds. What that means is if you have more than one carbon, so say we have the formula C3H8, carbons like to form bonds, chain bonds. So what that means is one carbon is going to be attached to another carbon, which is going to be attached to the third carbon. So they're going to form a chain. Then we would put the hydrogen atoms all around that chain. And we'll do some examples in class so you can see us putting these rules to the test. Next, you can count the total valence electrons. Sometimes I like to do this step first, just so I know how many electrons I have to play with. So to count the valence electrons of all the elements in the compound, we're going to look at where the element is on the periodic table. Based off where it is, we'll know how many valence electrons each one contributes, and then we can get the total valence electrons for that compound. This is important when we're making bonds because we don't want to use more electrons than we actually have available to us. We're sometimes going to be drawing Lewis structures for polyatomic ions. So if we happen to be drawing a structure for a cation, so a positively charged polyatomic ion, we would need to subtract electrons from that total valence electron count. For the anions, the negatively charged ones, the reason they're negatively charged is because they have extra electrons. So since they have extra electrons, we need to take that into account and add those electrons into our total valence count. And you'll see examples of this in the lecture videos. An example would be SO4 2-, the sulfate anion. Once we calculated the total valence electrons based off of the elements, we would need to add 2 more because of that -2 charge. The next step is to connect the central atom to the surrounding atoms with a single bond. So what that means is what you saw in the previous, where I had a carbon and then I drew a line to another carbon. That would be a single bond. This single bond, this line, represents 2 electrons. Then you place electrons as lone pairs around the terminal atom. So once you figure out what your structure looks like, your bare bones structure, everything's connected with single bonds, you might find that you have extra electrons left based off your initial calculation of your valence electrons. If you have extra electrons left, you want to start placing those on the terminal atoms first. So what we're trying to do is we're trying to make sure that every atom in that structure is happy. And how do we know if it's happy? If it has a full octet, if it has 8 electrons, if it has that noble gas shell configuration. So our goal is to try to get 8 electrons around every element. Of course, with the exception of hydrogen. Hydrogen only needs 2. So once you make the terminal atoms happy and they all have 8, then you focus on the central atom. So worry about the central atom last, because sometimes you can take valence electrons, electron pairs off of the terminal atoms to make double and triple bonds. And once again, you'll see that at work in the class lecture videos. So here's some Lewis structure practice that we're going to be doing in class. We will try some examples with one central atom, multiple central atoms, we'll do polyatomic ions, and then of course, like you've heard me say a million times already, there's exceptions to everything, and there's also exceptions to the octet rule, so we'll look at some examples where that applies as well. So why are we learning to draw Lewis structures? So the reason we're drawing Lewis structures is so that we can apply the VSEPR theory to them. So what the VSEPR theory is the valence shell electron pair repulsion. So what this does is it predicts the 3D shape of the molecules and of the polyatomic ions. This shape is determined by the repulsions of these electron pairs. So the lone pairs that we're drawing in these Lewis structures are going to determine the shape of the molecule itself. So here are the basic shapes. We have linear, bent, triangular, pyramidal, tetrahedral. There are more shapes, but these are just the main basic ones. And I'm going to go through them step by step and discuss each one. So there are 6 steps in drawing the shape. First step, of course, is to draw the Lewis structure. That's why we learned how to draw Lewis structures. We need to know where the electrons are in order to determine the shape of the molecule itself. Next, you count the things around the central atom. And when I say things, atoms count as one thing, and the electrons pairs count as one thing. So when I'm counting the atoms, it doesn't matter if it's a double bond, a single bond, a triple bond. I'm just counting the atoms itself, how many atoms are around the central atom, not how many bonds. Electron pairs also count as a thing. So if you have an electron pair around the central atom, that would also count. Next, you can draw the basic shape and indicate if there's any multiple bonds. Of course, you want to take into account lone pairs, and we'll adjust angles if and when we need to. For larger molecules, it's often easier to draw the shape for the central atom and then combine, because in larger molecules, there's more than one central atom. So you would have to figure out the configuration around each and then combine it all together. So let's start with the first category. If there are 2 things, it's going to be linear. So what do I mean by things? That's how many atoms or how many lone pairs are on the central atom. So an example would be carbon dioxide. Notice carbon is the central atom. It is bonded to 2 oxygens, both with double bonds. Now, if I'm counting the things around the central atom, carbon, I just have 2 atoms around carbon. 1 oxygen here, 1 oxygen there. So that's a total of 2 things. The fact that there's double bonds does not matter. I'm also not taking into account the lone pairs on the oxygen. I'm just focusing on the carbon itself. Whenever you have 2 things around the central atom, the shape is going to be linear, and the angle, therefore, is going to be 180 degrees. And we're talking about the angle from one oxygen all the way to the other. All binary compounds are linear. That means is if there's only 2 elements involved, it's going to be a linear compound. You don't have a central atom with a binary compound, but it's still linear. We'll see some examples of this in class as well as in lab. So on the handout supplied to you, that would be this category that we're looking at right now. So the first number is the number of things, and we said there were 2 things, 2 atoms more specifically. The second number, where we see a 0, that's how many of those things are lone pairs. So what we saw in the previous example, that there were 2 things around carbon, but both those things were atoms. So that means 0 of those things were lone pairs. So we follow this category over and see how to draw the shape. Of course, we would insert the symbols. We would put a C here, an O here, and an O here, not just dots. But we follow along and it tells us the name, linear, and it also gives us the angle. So we'll be using this chart to classify several different Lewis structures to figure out their shape. Next, let's look at what if there are 3 things. So for 3 things, trigonal planar is the basic geometry, but there are variations. So looking at 3 things, we have 2 shapes that it could possibly be. So if it's trigonal planar, if that's the shape, that means that the 3 things around it are all atoms. So the example I have here is boron with 3 fluorines around it. Notice boron has 3 atoms, but 0 lone pairs on it. So we're just looking at the central atom itself. When you have a trigonal planar shape, the bond angle is going to be 120. Okay, now imagine taking that shape and removing one of the fluorines. Okay, so if I removed an atom and replaced it with a lone pair, what we're going to get is a bent geometry as shown in this sulfur dioxide example. So here we have sulfur. It has 3 total things around it, oxygen atom being one thing, the other oxygen atom being another thing, and the third thing is a lone pair on the sulfur itself. So it has 3 total things, but 2 of those things are atoms and 1 is a lone pair. So due to 1 being a lone pair, that changes the shape. We now have a bent molecule, and the bond angle is going to be less than 120 now. Whenever you replace an atom with a lone pair, you have larger repulsive effects. So this is why the angle is decreasing. It's going to be less than 120 instead of 120, which the trigonal planar example had. So how do we find these shapes on the handout? Well, the first example, the boron trifluoride molecule, had 3 things around it, 3 atoms, 3 fluorines, and 0 lone pairs on the central atom. So that tells us that it's trigonal planar and the bond angle is 120. In the example of sulfur dioxide, there were 3 things around sulfur dioxide, 2 atoms and 1 lone pair. So the second number represented asks how many of those things were lone pairs, and our answer is 1. It had 1 lone pair. So we follow this category. It shows us the shape, tells us the geometry is bent, and that the angle is less than 120. So we are adjusting the angles using a less than or more than sign. So generally when we replace an atom with a lone pair, it's going to be less than. Lone pairs and multiple bonds need more space. That's why the angles are less, not more. Now let's look at four things. So the four things category, notice there's several different shapes it could be. So you really need to pay attention to how many of those things are atoms and how many of those things are lone pairs. So let's look at the first geometry. The first geometry is called tetrahedral. So this is the case where the central atom has four things around it and all of those things are atoms, so 0 lone pairs. In this case, the bond angle is 109.5. We'll notice the shape itself too. We're starting to draw in 3D. So the two hydrogens with the straight lines, the reason they have straight lines is because we're saying those hydrogens are in the same plane as the paper. This hydrogen down here is coming out of the plane of the paper. I know that because of this wedge. So you draw a wedge and then the atom to indicate that that hydrogen is coming out of the plane of the paper. A dashed line, therefore, represents the hydrogens going into the plane of the paper. We're doing a lab where we're going to be building some of these molecules with molecular models. And so you'll actually see what this looks like in 3D rather than just on a slide or a piece of paper. It is important to include dashes and wedges when needed. So now let's look at the second one. So if we took one of those hydrogens, if we took one of those atoms and replaced it with a lone pair, what we would get would be a trigonal pyramidal shape. So now we have nitrogen as the central atom. It has 3 atoms around it and 1 lone pair. So that lone pair is going to take up more space than a single bond. So notice our bond angle is going down, so it's going to be less than 109.5. This element, or compound I should say, in particular, its bond angle is 107. You don't need to memorize that angle, just know that it's going to be less than 109.5. The last shape is going to be bent. So in a bent shape, now we have taken 2 of the atoms and replaced them with lone pairs. So in this example, we have water. Water is going to have 2 hydrogen atoms around it and 2 lone pairs. So it still has 4 total things. It's just 2 of those things are lone pairs. This is going to make the bond angle even less than 109.5. So all of these categories are listed here. The first one, 4 atoms, 0 lone pairs, tetrahedral. Then in that next example, nitrogen trihydride, where there were 4 things, but one of those things was a lone pair. And then last but not least, 4 things, 2 of them a lone pair. That was the water example, and it was a bent shape. So you can use this handout to help you figure out the shape, how to draw it with the dashes and wedges, figure out the geometry itself, and also the angles. Now let's look at when there are 5 things around the central atom. So in the case of those 5 things being all atoms, the shape you would get would be trigonal bipyramidal. In this case, we have a phosphorus atom with 5 chlorine atoms around it. Notice there are 0 lone pairs on that phosphorus atom. You have 2 different bond angles, 90 and 120. So imagine taking one of those chlorine atoms, removing it, and replacing that with a lone pair. When that happens, the shape you will get is a seesaw shape. So you can see in the picture below that this looks kind of like a seesaw, like you would see at a park. These 2 F's being the base, and then the straight line across being the places where you sit. This is going to make the bond angles now be less than, because remember, lone pairs take up more space than an atom and a single bond does, so it's going to be making those angles less, pushing down on those fluorines more. So taking yet another atom away and replacing it with a lone pairs get us the T shape. So this would be 5 total things around the chlorine in this case. 3 of those things are atoms. 2 of those things, are lone pairs. And you'll notice when we draw the actual shape of these molecules, we don't include the lone pairs in the shape. So if you take away the lone pairs, you get the shape of a T, hence the name T-shaped. Next, we have linear. This is where there are just 2 atoms around the central atom and 3 lone pairs for a total of 5 things. So you have a linear molecule from the fluorine to the xenon to the other fluorine. Last but not least, we have a 6 things category. We are probably not going to see anything in this category for this course, but I do want you to be aware of the category. So I'm going to go through these rather quickly. We have octahedral when there are 6 atoms. Not sure why it's called octahedral since octa means 8, but there you have it. So this would be where there are 6 atoms around the lone pair. We get square pyramidal when we have 5 atoms and 1 lone pair. And then last but not least, square planar when there are 4 atoms and 2 lone pairs. So why do we want to know the shape of a molecule? How does it help us to know that a certain molecule is trigonoplanar versus trigonopyramidal? Well, this is going to help us figure out its polarity. So far we've figured out or used electronegativity values to determine whether a covalent bond is polar or nonpolar. But what we were looking at is just the bond itself, not the molecule as a whole. So we figured out that one specific bond based off the electronegativity values. So we subtracted them and then used this chart here to figure out if it was nonpolar or polar. Which range did it fit in? Well, now what we're going to do with the structures, the geometry, we're going to use it to determine whether the entire molecule is polar or nonpolar. Because you can actually have polar bonds on a molecule where individual bonds are polar, yet the molecule itself is nonpolar. So the geometry is going to help us figure that out. So one way to figure this out is by calculating the net dipole. So what a dipole is, it's a separation of charges between 2 covalently bonded atoms. We represent it by vectors, and the vectors that I'm speaking of are the arrows in the picture below. So usually what we have is the arrow points towards the more electronegative atom. So in this case of carbon dioxide molecule that we have below, oxygen is the more electronegative atom, so we would draw a vector pointing, or an arrow pointing toward the oxygen. Well, that's just one of the bonds. There's another bond going from carbon to another oxygen. So we would then draw another vector pointing towards the oxygen because oxygen is more electronegative than carbon. So in the case of this carbon dioxide molecule, what happens is those vectors cancel each other out because we have one going to the right and one of equal magnitude going to the left, making them cancel. So when the vectors cancel, we get no net dipole, 0. Okay? So if we have no net dipole, that means the molecule itself is nonpolar. So even if that carbon-oxygen bond is polar, the molecule as a whole, since the arrows cancel, is nonpolar. So let's look at when the arrows don't cancel. So in the example of water. So water, H2O, is a polar compound. So how do we figure that out? Well, we can figure it out one way by using this net dipole method. So between hydrogen and oxygen, so looking at just one of those bonds, oxygen is more electronegative than hydrogen. So once again, I'm drawing an arrow pointing towards the oxygen. Well, I need to do it to all bonds present, so I do it again to the other hydrogen-oxygen bond. So now, notice since this molecule is bent, because when we draw the Lewis structure, we go through all the steps to figure out the shape, we'll see that that oxygen atom actually has 2 lone pairs on it. So that oxygen will have a total of 4 things around it, 2 of those things atoms, 2 of those things lone pairs, giving it a bent shape. So since it has a bent shape, now the vectors don't cancel each other out. So imagine picking up these arrows and adding them from head to tail. So I'm going to take this first arrow that goes in this direction. Okay, so that's this arrow here. Then I'm going to pick up the other arrow and add it to this one. And you always add arrows or vectors head to tail. So that arrow is going in this direction. So notice they're not canceling each other out. We have a total net dipole from the very tail of the arrows to the head of the arrows. So if we have a dipole, if the arrows don't cancel each other out, that tells us it is a polar molecule. Another way to figure out if the molecules are polar or nonpolar is by applying the rules on the following slides. So for this first slide, we're talking about nonpolar molecules. So you can actually apply these rules to the Lewis structure. You don't even have to know the molecular shape of it. So the first rule says molecules that have no lone pair on the central atom and all terminal atoms are the same, it's going to be nonpolar. So there's two examples shown here. So I have carbon tetrachloride, so carbon with 4 chlorines around it. So it is a molecule and it has no lone pairs on the central atom, no lone pairs on the carbon. And all the terminal atoms, so all the atoms that's attached to it, are the same. They're all chlorines. So that means this is nonpolar. I don't even have to draw my vectors. Just with those rules, I can tell you it's nonpolar. However, if you have a central atom with no lone pairs, but the terminal atoms are not the same, so if I replace one of these chlorines with a hydrogen now, looking over here, I've now changed the game. It's now going to be polar. So you need to make sure it fits both. No lone pairs on the central atom and all terminal atoms the same. Let's look at the next rule. So molecules that are made up of only carbon and hydrogen are always going to be nonpolar. So what that means is if you only have carbon and hydrogen present, no other elements, so if you throw in an oxygen or a nitrogen or anything else, this doesn't apply anymore. But if it's just hydrogen and carbon, it's going to be a nonpolar molecule. It doesn't matter if you have 52 carbons and 87 hydrogens, it's still going to be nonpolar. This is very helpful because a lot of hydrocarbons, that's what compounds with carbon and hydrogen only are called, hydrocarbons. With hydrocarbons, they often get to be very, very long chains. So you can have extremely large molecules. And in that case, it's going to be really hard to try to draw the shape, figure out all the vectors. So this one's very useful. Saves you a lot of time. Last but not least, diatomic molecules with 2 atoms of the same element. So if you have a hydrogen and hydrogen attached to each other, their electronegativities cancel each other out, so it's going to be nonpolar. Same goes with any of the other diatomics. There are actually 7 elements on the periodic table that exist as diatomics in nature. Hydrogen, oxygen, chlorine, nitrogen, and the rest of the halogens as well. So now let's look at some rules we can apply to figure out if a molecule is polar. So molecules that have 1 lone pair on the central atom, or when all terminal atoms are not the same. So we've looked at this second example already. Okay, this was the no lone pair example. When we replaced the chlorine with a hydrogen, we said, okay, now it's polar. But the first part of this rule says if there's a lone pair. So no matter what, if you see a lone pair on a central atom, it's going to be polar. So you don't even have to know the shape yet. You can just have the Lewis structure and see, hey, there's a lone pair, it's polar. The next rule says molecules with more than 1 lone pair on the central atom are usually polar. So most of the time, 90% of the time, but there are some exceptions. Water is not an exception. Water is a polar molecule. You can see in the example, there are 2 lone pairs on that central atom of oxygen, making it polar. And you couldn't see it, so going back over to this nitrogen trihydride example, it might be hard to see, but there is a lone pair on the nitrogen, so that's why nitrogen is polar. There's a lone pair on the central atom, causing it to be a trigonal pyramid. Couldn't think of the name. All right. So taking this a step further, because we're always adding on. Once we know the polarity, this is going to help us figure out some other pieces of information. It can help us with determining solubility, melting points, and boiling points. So there's two types of forces occurring within molecules. So there's intramolecular forces, and these are attractive forces within the molecule itself. So the chemical bonds that determine the shape, all of that. Okay, we're not going to be focusing on intramolecular, what's going on within the molecule itself. What we're going to focus on is intermolecular, so ER, intermolecular. Now these are attractive forces between two different molecules. So for instance, say you had a water molecule and a sodium chloride molecule. We would be looking at the intermolecular forces, so the forces between that sodium chloride and that water molecule. Why are we focusing on this? Because intermolecular forces determine solubility, melting points, and boiling points. So we're going to be able to, knowing the structure and the shape and the polarities of molecules, we're going to be able to predict if they're going to be soluble in one another. We're going to be able to predict which one's going to have the higher melting point or boiling point. A general rule for melting points and boiling points is that polar compounds will be higher than nonpolar. And actually, ionic will be the highest. So it goes ionic, highest melting points, polar in the middle, and then nonpolar having the lowest. Melting point and boiling points depend mainly on three things. The first thing being polarity. And this is the most important. This is the one that's going to affect it the most. So the polar compounds, polar covalent compounds, will be higher than nonpolar. So looking at this example here, we have carbon dioxide versus water. Okay, so carbon dioxide, we saw this in a couple examples actually, and we saw that it was a linear molecule and that it was nonpolar. So I'm going to write NP for nonpolar. Now water, we said, was bent because it had two lone pairs on the central atom being oxygen, and so it was a polar molecule. So if I know the polarities, carbon dioxide being nonpolar and water being polar, I can figure out just from that which one's going to have a higher melting point and boiling point. The polar one will. So that means water is going to have a higher melting point and boiling point than carbon dioxide. And we can actually see this is true because at room temperature, water is a liquid. And carbon dioxide is a gas. So if it's a gas, that means that its boiling point is very, very, very low. Number two, the intermolecular attractive forces. So these were the forces between the molecules. Now the intermolecular forces depend on polarity. So they both fall into the same category. So if we know the polarity, we know what the intermolecular forces are. So it's not something we necessarily calculate, we just use it to figure out polarity. Last but not least, molecular mass. Now we're only going to apply molecular mass if the polarities are the same. So what I mean by that, if we have two nonpolar compounds and we're trying to figure out which one has the higher melting point or boiling point, then we would resort to calculating the molecular mass. So we'll learn to calculate molecular mass in the next chapter. The larger the mass, the higher the melting point or boiling point. And here is that chart I was talking about on the previous slide. Remember that ionic has the highest. So if you are looking at two compounds and one of them is ionic and the other is covalent, the ionic one will have the higher melting point and boiling point. If you're looking at two covalent compounds, that's when you need to figure out their polarities and use that to predict which will have the higher. So now we've looked at melting point, boiling point, let's look at solubility. So solubility is the maximum amount of substance that can dissolve in a given amount of liquid at a certain temperature. So we actually tested solubilities in lab 4 when we were seeing our unknowns solubility in water. So did they dissolve in each other or not? So how are we going to use polarities to figure this out? Well, we're going to use the general rule that like dissolves like. What that means is polar things will dissolve in polar solvents. Nonpolar compounds will dissolve in nonpolar solvents. So if we're trying to predict if two things are going to be soluble in one another, we look at their polarities. If they are both polar, then yes, they are soluble. If they are both nonpolar, then yes, they are soluble. If one is polar and one is nonpolar, then no, they will not be soluble in one another. Let's use the example from the previous slide. We looked at carbon dioxide and water. Carbon dioxide we said was nonpolar. Water we said was polar. So one's polar, one's nonpolar. So are they going to be soluble in one another? No, they won't, and they're not. So carbon dioxide, think of carbonated beverages, soda. Okay, that carbon dioxide is not dissolved in the soda. That's why when you open a can of soda, you hear that sound, because as soon as you open it, what's happening is those carbon dioxide bubbles are trying to escape because they're not soluble in the liquid. That's why soda cans need to be pressurized, because they're trying to force the carbon dioxide into that liquid. If you leave the can open, eventually all the carbon dioxide is going to escape, leaving you with a flat soda. They are not soluble in one another because they have different polarities. So here are some practice problems that we are going to be working on in class. So watch the class videos to see those worked through. We'll focus on not only drawing Lewis structures and coming up with their molecular geometries, but also using their geometries to figure out their polarity and then applying that further to what we now know about predicting the melting points, boiling points, and solubilities of different pairs.